Welcome back, folks. In this video, we'll be looking at what are called Laurent series in complex variables. Okay. So from the last video, we looked at if we have a function that's analytic, we can formulate a Taylor series of positive integers. Okay, that was the whole point. So it's a power series whose powers in the said series are positive. Okay, so the question now becomes this. So we want to ask ourselves this question: if a function f of z fails to be analytic, can we formulate a power series? Can we formulate such a power series? And the answer is yes. Yes, we can. By using another type of series called the Laurent series. So, some terminology to go over before we talk about what a Laurent series is the following. So if a complex function fails to be analytic at, let's say, oh shoot. Analytic at z equals z naught, let's say. This point is called an isolated singularity. It's called a singularity, not isolated singularity, sorry. It's called a singularity. Or they call it a singular point, okay? So as just a quick example, if I have a complex function z as z over z squared plus 9, right? So in the complex numbers, this function is analytic except at points z equals minus 3i and then z equals positive 3i in the terms of the complex numbers, right? So as an example, this function fails to be analytic at two complex numbers, minus 3i and then positive 3i, right? So we call these singular points, or just a singularity. Okay. Another function that we have seen in previous videos is the principal logarithm. So the principal logarithm of z also fails to be analytic along points where the real part of z is negative, right? So that referred to the principal branch cut of the natural logarithm, right? So oh shoot, the angle, right? So the principal argument. So we left out minus pi, okay, minus pi to pi. Okay, so that referred to the principal branch of the logarithm, right? So, okay, those are examples of points that are singularities, okay? So we are going to focus on deriving an infinite series dealing with isolated singularities. Z equals Z naught, okay? And then a definition is what an isolated singularity is. So f of Z has an isolated singularity if there exists a punctured disk. Punctured disk means it's a disk without including the center of the disk. So it's a punctured disk that is open. So it's not including the boundary. So a punctured disk looks like this mathematically. Okay. So Z minus Z not being positive, you're not including the center of the disk, Z naught. Okay. And this is where f of Z is analytic. All right, so where f of Z is analytic. So basically, right, so you have Z naught and so you're not including the center, but the radius, you're not including the center of the circle, and you're not including the boundary either. So this is what I'm referring to as the punctured open disk. Okay. And so it's everywhere analytic except at the center. Okay. All right. So as an example, so if we go back here into the couple of examples. So not only so in part A, Z equals negative 3i and positive 3i are singularities. They're also isolated singularities, okay? So here is 3i. Oh, shoot. That's the wrong point. 3i is here. Then minus 3i is here, right? We can figure out a circle. So minus 3i, let's say less than 1, right? And then Z minus negative 3i is less than 1. So we can figure out a punctured open circle, right? So with radius 1, right? So it's something like this. It's minus 2i minus 4i, and this is 2i and then 4i here. Minus 1 and positive 1 there. Oh, okay. I meant this is an open disk. So we can figure out two circles which don't include the other singular point, right? So in this case, 3i minus 3i are isolated singularities, right? So these are isolated singularities. These are also isolated singularities, okay? Right, they have their own separate punctured disk where f of Z is analytic, right? However, on the principal logarithm function, the singularities there are not isolated. Okay, they're not isolated. Okay, so we're looking at points where the negative real axis and 0 are not included, right? And everywhere else is analytic, right? So if we draw in a punctured disk, let's say at 0, well, we're going to include more points that are singularities, primarily like these points in here, right? So so singularities of the principal logarithm are what are called non-isolated singularities. Isolated being like single, you're the only one there, right? It's not isolated. There is at least one point on the negative real axis that is a singularity, right? That fails to be analytic, right? So there are non-isolated singularities. All right. So, okay. So hopefully get those down. So, and another thing is if z equals z naught is a singularity, of a complex function f of z, then f of z cannot be expressed as a power series. Right? However, but if z naught is an isolated singularity, okay, it's possible to represent f of z as a power series. Okay, so if your singularities are isolated, it is possible to express a function, an analytic function, as a power series. Okay, and so here is what a Laurent series is. Okay, so you're going to express a series as infinite powers of exponents. So I'm going to write out the series like this: z minus z naught squared plus a to the minus 1 over z minus z naught plus a0 plus a1 times z minus z naught plus a2 times z minus z naught squared plus, and this keeps going. Okay, so a couple things to mention about this series. Okay, this is what's called a Laurent series right here. A Laurent series. So this has two parts. The first part deals with the negative coefficients of this series. And this is what's called the principal part. The principal part of a Laurent series. Okay. The other portion here, on the other hand, this is what's called the analytic part. The analytic part of a Laurent series. Okay. And this kind of goes back to looking at the circle of convergence of a power series, right? If we have a power series like this, k equals 0 to infinity, all right, there was a certain threshold on where to show the circle of convergence, right? And the radius of convergence. So typically this will converge on a circle of convergence like this, right? Z minus Z naught being less than R, okay? Also, we're going to have the same type of situation when we're dealing with the principal portion of the Laurent series, right? So this is a to the minus k over z minus z naught to the k power, right? So what we want to show is, so we want to find a, so the goal here is we want to find a radius of convergence. R. So that 1 over one over the absolute value z minus z naught is less than, I'll say, r star, right? So basically your circle would be will have an inverted radius. Okay. So what it turns out is a Laurent series will have what is called an annular domain. Okay. So what this means is that a Laurent series will have a annular domain as the set of convergence. Right. Okay. And it kind of looks at the similar way on how we would arrive convergence of an ordinary power series, right? So if we know that z minus z naught has to be less than r, right? There is some other number for which if we do an inversion, right, 1 over z minus, if we do an absolute value of an inversion of points, 1 over z minus z naught, well, it could be 1 over capital R, but it could be some other value, right? R star, right? It does not necessarily mean it's 1 over R, right? Um, so basically we'll have an annular domain where a Laurent series will converge. Okay, so if your center of your Laurent series is at z equals z naught, so we'll have a little r here and then big R here. And this is where it converges. Okay. Um, so in order to formulate a Laurent series, so in order to formulate a Laurent series, you want to start off with a Taylor series. You know, and multiply extra terms to formulate the result. That's sort of the idea in formulating to formulate a Laurent series. Okay, so I'll show you an example. So so what if I want to expand this function f of z equals e to the minus 1 over z squared, where absolute value of z is greater than 0. Okay. And so we want to expand this as a Laurent series. Okay. So first of all, what you want to do is draw out a picture, see what this looks like. Okay. So if I have the complex plane here, and then we know that e to the minus 1 over z squared, this is analytic except at z equals 0. So we're going to have a singularity at 0. But everything else, it's going to be a disk where the modulus of z is positive. So really, it's just all the points on the complex plane except at z equals 0. Okay. So we want to formulate a Laurent series for this. But we do know the Taylor series for e to the z, or I should say the Maclaurin series for e to the z, right? The Maclaurin series for e to the z is equal to 1 plus z squared over 2 factorial plus z cubed over 3 factorial and so on, right? Okay, so term by term, e to the z looks like this, right? The Maclaurin series of e to the z looks like this. Okay, so if I want to look at the derivation of e to the minus 1 over z squared, well, just plug in 1 over z squared for each z term in the Maclaurin series, right? So it'll be 1 plus minus 1 over z squared plus minus 1 over z squared over 2 factorial plus minus 1 over z cubed over 3 factorial plus. This pattern keeps going, right? And so this series would equal to 1 minus 1 over z squared plus 1 over 2 factorial one over z to the 4th minus 1 over 3 factorial times 1 over z to the 6th. Okay. Plus, and this keeps going, right? So this here is a valid Laurent series. Okay. So, so these terms right here, this will account the principal part, the principal portion. This here is the analytic portion, the constant. Okay. So that's a valid Laurent series. Okay. So, and here's just a great theorem on computing the coefficients in the Laurent series. And this is what's called Laurent's theorem. Laurent's theorem. Okay, so let f of z be analytic within within an annular domain. Right, within this annular domain, right? Then f of z equals to a Laurent series. And this is valid along this angular domain. And to compute for the coefficients a sub k, this will equal to 1 over 2 pi I times the integral of a closed contour of f of s divided by s minus z naught to the k plus 1 ds, excuse me, ds, where k equals 1, plus or minus 1, plus or minus 2, and so on. Okay, C is a closed contour. Lying entirely in D with Z naught as its interior. So basically the illustration here is so if I have some D domain and Z naught, and then this is the bigger radius and the smaller radius is here. We can formulate a Laurent series along this angular domain, right? And then C is basically this curve and grain, right? So we can formulate the coefficients by using a closed contour, right? That's in D and that has Z naught as its interior, okay? And this refers to the Cauchy integral formula and how you would show that. So in these next few minutes here, I'm going to go over some numerous examples on formulating Laurent series. Okay. Formulating a Laurent series. So the rule is we want to start off with a Taylor series and then build off the Taylor series of what we know into formulating a Laurent series that we want. Okay, so if that doesn't make sense, I'll show you what I mean by working out these examples. Okay, so expand. So this function, 1 over z times z minus 3 as a Laurent series. For the indicated annular regions. Okay, so we have one of them here like this. Part B is and then part C is this one. All right. So if you want to, you can pause the video and try to figure out how we could expand this function as a Laurent series for each of these different annular domains. Okay. So try to pause the video and think about this. Otherwise, if you want to stick around and watch me do this work, you can do that too. So first of all, let me move these out of the way. I'll use these a little bit later. Put this here. Okay, so we want to look at this first. So we have our function f of z equals to 1 over z times z minus 3. Okay, so our domain, so our region that we're concerned about, so it has a center of radius 0. So it's going to be a puncture disk at 0. And we are including the circle radius 3, right? So here, here, and there. All right, so this is the puncture disk they are referring to. All right, so it's okay. So f of z fails to be analytic at z equals 0 and then z equals 3, right? So this function fails to be analytic at 0 and at z equals 3, which is that point right there, right? So we're not including these points. We're also not including the boundary. So this here, this disk is an isolated. This would show that z equals 0 is an isolated singularity. Okay, so we can formulate a Laurent series. So what we want to do is so since the absolute value of z is less than 3, we want to formulate a Taylor series. I should say a Maclaurin series. That's a lot easier. Maclaurin series. All right. So we want to figure out a Maclaurin series where the absolute value of z is less than 3. Okay. We have some part of this in our function, right? 1 over z minus 3. Okay. So if I express f of z equals to 1 over z time, hold on a second. Yes. Okay. So yes. So we want to formulate a Maclaurin series where the absolute value of z is less than 3. So in other words, so we want to formulate a geometric series where the modulus of z over 3 is less than 1. Okay. Let's see where we can go from here. So if I write out f of z as a product, z minus 3. Z minus 3. Okay. And so I'm going to factor out a minus sign in this term. So I can also re-express f of z as minus 1 over z times 1 divided by 3 minus z. Okay. All right. So something like this. Now, if you notice, this looks somewhat familiar, right? Okay, so if I factor just one more term, let's say a 3, right? So I can express this function one more time as minus 1 over 3z times 1 over 1 minus z over 3. Okay, something like this. Well, we can formulate a Taylor series for this quantity, 1 over 1 minus z cubed. And that is what I was referring to in this fact right here. So in order to formulate a Laurent series, you want to start off with re-expressing your function first in order to fit in a Taylor series. Okay. And then you can use that to build off on what a Laurent series for a function would look like, right? So that's what I'm doing here. So, okay, so we formulated what we expressed on what f of z could equal to, right? And this, we can form a geometric series. A geometric series. So this would equal to minus 1 over 3z times the geometric series. 1 plus z over 3 plus z over 3 squared plus z over 3 to the fourth plus, and this pattern keeps going, right? So this would equal to, well, minus 1 over 3z, minus 1/9 minus 1/27 x minus 1 over 81 x squared minus 1 over 243 x cubed minus, and this keeps going, right? So this here is a Laurent series, right? Or Laurent series. Okay. This right here is the principal, and this quantity right here is the analytic portion, right? Okay, so that's the whole idea, right? So let's look at part B, shall we? So part B was we wanted to formulate a Laurent series for this angular domain, right? I scroll down. All right. So we want to formulate a Laurent series for this angular domain. So it's a good idea to draw what these pictures look like, or what these regions look like. So we have a circle that's at the radius of 3. So 1, 2, 3. So we know the function's not analytic at that point. So and the radius is at 0 and it's up at 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, and then 1, 2, 3. Okay, so here's our region now. And now this time, so our function fails to be analytic at z equals 0 and z equals 3. So we are still dealing with a puncher disk, but this time it's at the circle of, so the puncher disk is at z equals 3, right? So let me write out what f of z is. So now, this time, our region is at the puncher disk, centered at z equals 3. All right, so what I'm going to do now is I can express f of z as a product, but a product now will look like this. So if I write out z minus 3 times 1 over z. So now this time we want to formulate a Taylor series. When I meant Maclaurin series. With this circle of convergence, right? Okay, so if I look at 1 over z here, right? So this equals to 1 over z minus 3. And I can write out this product as 1 over z minus 3 plus 3. Okay? Just to compensate what 1 over z equals to, right? So if I add 3 and subtract 3 in the second term, and then express that as 1 over z minus 3 times 1 over 3 plus z minus 3. Okay. I can formulate a Maclaurin series for the second term, right? So we want our geometric series to be less than 1. Z minus 3 over 3 needs to be less than 1. So that will be how we would form out the geometric series for this term. So if I write out this as 1 over z minus 3 times 1 over 3 times 1 plus z minus 3 over 3. Okay, then I will get my geometric series. So this will be 1 over 3 times z minus 3 times 1 over 1 plus z minus 3 over 3. Okay, and so this equals to 1 over 3 times z minus 3 times 1 plus z minus 3 over 3 plus z minus 3 over 3 squared. It's plus, so it's alternating. Crap. All right, so this is a minus, this is a plus, minus z minus 3 over 3 cubed plus z minus 3 over 3 to the 4th minus, and this pattern keeps going. Okay, so this Laurent series will equal to 1 over 3 times z minus 3 minus 1/9 plus 1/27 times z minus 3 minus 1/81 z minus 3 squared plus, I know it's amazing, 1 over 243 times z minus 3 cubed minus, and this keeps going. All right, so this is a Laurent series for part B. Okay. So hopefully that made sense. Now part C is going to be a little bit trickier. Let me move this down below. Now part C is going to be a little bit trickier. Okay. So what we want to do is formulate a Laurent series for f of z equaling to 1 over z times z minus 3. Okay, along this angular region. Okay, so let's draw out the region, see what it looks like. So we know that the circle, let me actually draw this a little bit bigger. I need more hash marks here. So here's the complex plane. And we know that the circle has a radius of, it's in between the circles of radius 1 and 4. So I want to see if I have enough here. So 1, 2, 3, 4. So it's going to be restricted between the circle of radius 1. So right here. And the circles of radius 4. So this region right here. So in this case, it's analytic, except at z equals 3 and then z equals 0, right? And so everywhere else, this is where it's analytic. So they're talking about this annular region here. Okay, so this one's going to be a little bit trickier, okay? If we see a less, a less than sign, if we see a less than sign here, what you want to do is, I don't need that. If I see a less than sign here, that will indicate that we need to formulate. So we're going to need to formulate a Maclaurin series for the upper portion of this domain, right? Okay. The greater than sign, on the other hand, that will constitute the principal portion. Okay. So what we need to do is we need to also formulate a, let's say, Maclaurin series where z minus 4 is greater than 1. Okay, so what I'm saying here is that the greater than portion, right? So the lower circle here, that will constitute the principal portion, right? As opposed to the upper range of your domain, that will concern with a analytic portion, right? So nevertheless, we're going to have to formulate a Maclaurin series for the terms where the absolute value C of z minus 4 is less than 4, and the absolute value of z minus 4 is greater than 1. Okay, so what we're gonna need to do is we're going to use partial fractions decomposition. For f of z equals to 1 over z times z minus 3. Okay, so on the smaller circle, we know that it's so it's analytic not at z equals 3, right? So actually that's not important, but we're going to use partial fractions decomposition to re-express what f of z is as a sum. Okay, so by using partial fractions, a over z minus 3 plus b over z, let's say, right? And if we multiply both sides of the equation by the product of the denominator, right, we'll get that 1 is equal to a times z plus b times z minus 3, right? So if z equals 0, we'll have that b is equal to negative 1/3. And if z equals 3, we'll get that a is equal to 1/3, right? So we can express f of z as a sum of two fractions, right? So 1/3 over z minus 3 minus 1/3 over z. Okay, so what we're going to do is, all right, so since the function is analytic except at z equals 3, and z equals 3 is on the boundary of the green circle, this will deal with the so I'll call, so this will formulate the Taylor Maclaurin series. I'll just call it Maclaurin series for x minus for being greater than 1. On the other hand, the function is analytic except at z equals 0, and z equals 0 is on the boundary of the big circle. And so this will deal with the Maclaurin series for x minus 4 being less than 4. Okay. So let's write out f of z equals to 1/3 times this product, 1 over z minus 3, and minus 1/3 times 1 over z. Okay, so I'm going to label these quantities here. So I'll label this as F1, and I'll label this guy as F2. All right. So for the first F1 quantity, notice here, we can express 1 over z plus 3 as 1 over z minus 4 plus 1. Okay. I meant z here. Those are z's. Okay, so yeah, we can express 1 over z minus 3 as this quantity, 1 over z minus 4 plus 1, right? Right, z minus 3 is equal to z minus 4 plus 1, right? So this will equal to 1 over, if I just rearrange the terms a bit, so this will be 1 plus z minus 4, okay? And okay, and so what this will equal to is a geometric series, right? So 1 plus z minus 4 plus z minus 4 squared plus z minus 4 cubed plus yada, yada, yada. This pattern keeps going. And this converges where, okay, let's see. Okay, no, I want this to be greater than 1. What am I doing? All right, hold on, back up. I gotta see, I just work on these problems and don't look at my notes. I'm just working too fast. I'm just so excited. Okay, so we want to formulate a Maclaurin series for this quantity, whereas the absolute value of z minus 4 is greater than 1. So, okay, if I write out what I had before, so 1 plus z minus 4, and if I factor a z minus 4 quantity to each term on the bottom, so I will have 1 over z minus 4 plus 1, right? So this is 1 over z minus 4 times, I'm going to rewrite this other term as 1 over, I'm going to rewrite the bottom here as 1 plus 1 over z minus 4. Now I can write this quantity as a geometric series. So this equals to 1 over z minus 4 times 1 plus 1 over z minus 4 plus 1 over z minus 4 squared plus 1 over z minus 4 cubed plus, this pattern keeps going, right? Okay. So this is what F1 equals to. All right. On the other hand, okay, so F2 now. So for F2, so I have 1 over z. So we want this to be, so we want to formulate a geometric series where the length of z minus 4 is less than 4. Okay, so if I can rewrite 1 over z as 1 over z minus 4 plus 4, right? And so this equals to 1 over 4 plus z minus 4. Okay. And so if I factor out a 4 to each of the terms on the denominator, okay, in the denominator, so I'll have 1 over 4 times 1 plus z minus 4 over 4. Okay. And so this equals to 1/4 times 1 over 1 plus z minus 4 over 4. And so this equals to 1/4 times 1 plus 1 minus. Oh, and I should change the signs here and then here, since we have a plus here. So the signs are alternating. And that should be a plus there too. Okay. So this is 1 minus z minus 4 over 4 plus z minus 4 over 4 squared minus z minus 4 over 4 cubed. Okay, plus, and this pattern keeps going. And that is the Laurent series, right? So altogether, f of z is equal to 1/3 times, so I'm going to write out, so 1 over z minus 4 times 1 minus 1 over z minus 4 plus 1 minus z minus 4 squared minus 1 over z minus 4 cubed plus yada yada. And then this will be minus 1/3 times 1/4 times 1 minus z minus 4 to the 4th plus z minus 4 to the 4th squared minus z minus 4 to the 4th cubed plus so on. Okay. All right. So that, ladies and gentlemen, and everyone else, is the Laurent series for this domain here. Okay. All right. So, wow, that was a lot of work. So, hopefully that makes sense. Okay. Last example I'm going to go over is this one. So, expand. Okay, how about this one? So if you want to, try to pause the video and try to work on this example, okay? But otherwise, let's see what we can do here. So the best idea to approach this, the best way to approach this is to draw a picture and see where our function is defined on, right? So we know that z is this function right here. This is analytic except at z equals 0 and then z equals 1, right? Z equals 0 and z equals 1. So it fails where this is analytic, right? So so we know our puncher disk will look like a circle of radius 1, right? Circle of radius 1. Every point that's in that circle except at the origin, right? Okay. So so what we want to do is formulate a Taylor series. Or in this case, a Maclaurin series. A Maclaurin series at this section of this region, right? So if you notice, I'm going to write out the function as 1 over z times 1 over 1 minus z squared. Okay. And notice that 1 over 1 minus z, well, that's just the geometric series, right? 1 plus z squared plus z cubed plus z to the fourth plus, and so on, right? Okay. And also, if we were to differentiate both sides of this equation, d dz, not d dx. Gotta remind myself I'm doing complex differentiation. So this derivative would equal to, in this case, 1 over 1 minus z squared, right? That's the derivative. And so this equals to 1 plus 2z plus 3z squared plus 4z cubed plus so on, right? By using term-by-term differentiation. And we know that the original series would converge on points z where the absolute value of z is less than 1, right? So what we have is this series, right? This is the derivative, okay, in terms of the summation. We know it also converges on this set, right? So that's good, right? So we can write out f of z as this. So it'll be 1 over z times the sum. 1 plus 2z plus 3z squared plus 4z cubed plus so on, right? Then multiply by 1 over z, and you'll get 1 over z plus 2 plus 3z plus 4z squared plus so on. Okay. This is the principal portion. Shoot. So the principal portion, and this here is the analytic portion. All right. So hopefully that makes sense. And here's some problems for you to work with. Some suggested problems for you to work on. As always, please let me know if you have questions, and I hope these videos are helpful. If they are, make sure you like it. Make sure to subscribe, okay? So I hope you enjoy these videos. So for next time, we'll be looking at different zeros of complex functions. So we're looking at, we're going to observe what poles are, what isolated singularities are, what our removable singularities are. It's going to be great. So we are right at the thick of this course here. So, but other than that, I will see you all in the next video. So take care.